actually going to be a use of the Bernoulli equation. So we're starting on Bernoulli equation. What Torricelli theorem is about is it's talking about if you had, for example, alright, so this is this situation. Now let's say that it's filled with water, and it's an open balloon, and then one spring at the bottom. Okay, what happens is our Bernoulli equation is going to simplify it down. Right, let's think about what thing might be constant here is what equal pressures are flowing. Now, I know what you're thinking, but you can do even better than that. Now, if we think about our flow rates here, the flow rate going down here has to equal the flow rate coming out here. You are exactly correct. But we know that it's going to be area times velocity is going to equal area times velocity. Now, this area here is going to be way, way bigger than this area here, which means that this velocity, since the area is huge, relatively speaking, that means the velocity is going to be basically zero, okay? Because in this relative situation, the area is basically zero, okay? So for that reason, what we can do is we can get rid of this term here, since the water is basically not moving at the top there, okay? Now the last thing we can get rid of is if we redefine h to be the difference, this guy here. So h is really going to be standing for how far below the surface of the water is, the water that holds. All right. Now you don't need to worry about the middle of the hole or anything like that, because those are all going to be a single point. Hey, so what is going to happen is this is going to simplify into a rho GH is equal to 1/2 rho V squared. That's it. This should be familiar, this creation of energy. In fact, we can even do a little better. The density isn't going to change in this fact, so just GH is equal to 1/2 V squared. Now, you don't have to really memorize this, just a boiled down version of the Bernoulli equation. Right? If you type in Torricelli theorem, you're going to see a bunch of lovely pictures with a container of water with holes in it. All right. So this one's sprayed out like that. This one will spray out. It'll be going a little slower. This one will be going out a lot slower. So that's what we like to show as a visual for this kind of thing. Does that make sense? Yes. The bigger the difference in height, the bigger the velocity will be. This one has a very little difference in height, so it's going to have a low speed. V is little. We'll just say little. And this one, V equals big. Sounds awesome. All right, so we're going to do a little bit of practice with this. Okay, so for each one of these guys, I printed the Bernoulli equation. 1, so I don't have to write it, and 2, because it's all coming from here. All right, so we have a tank containing water with a height of 1 meter at point P right there. There is a hole. What is the speed of the water flow at the hole? Okay, so I like to approach it from Bernoulli. The pressure is going to be constant the whole time. This guy isn't going to be moving, really. I mean, yeah, a little bit, but not much that we care about. And I'm going to figure out the change in height. So for water, oh, well, let's just get rid of the density of water because it doesn't matter. So we've got 9.8 times the height. Now, because we're using delta height, because we have to pay for it, crossing this one out, we're talking about this height here. So 80 centimeters to 1 meter. So we have 20 centimeters or 0.2 meters, right? We got to use meters because we have gravity involved. And then equals 1/2 times v squared. Solving for v, quick maths here, is 1.98 meters per second. And that's it. That's the whole thing. All right, let's do another one. See if you can figure it out here. Give you a head start. Don't take too long. I'll be waiting for you. Large tub of water contained, and there's a faucet as shown in the picture. The water velocity out of the faucet is ellipsis. All right, pressure is constant. Velocity doesn't matter. That doesn't matter. Cross out the row your boats. So we're going to have 9.8 times our h. Our h is going to be 40 to 85 is going to be 0.45 meters. It's equal 1/2 times v squared. V squared is what we're looking for. Plug it in, and we have a 2.97 meters per second. Easy. All right. Last one here. Okay, a tube with a height of 100 centimeters water, a hole Q is located 10 centimeters above the ground. What is the horizontal distance x? We're looking for when the water will hit the ground. A little bit different, but you're supposed to know this stuff anyways. You only got how many days left, right? Hey, pause the video, see if you can figure it out. Okay, I'm going to catch up to you now. Pressure stays the same. Velocity doesn't matter. Height there doesn't matter. Rho doesn't matter. So G is 9.8 times H. The height is 0.9 meters. That's going to equal 1/2 times V squared. Our velocity is going to be 4.2 meters per second. All right, but that's not all. That's your velocity here. We are looking for this displacement here. So this is going to be like those old equations where you drive the truck off the cliff or run off the edge of the pool or all that stuff. So do you remember how to do this? I hope so. So we're going to use an old friend. D is equal to D0 plus V0t plus 1/2 AT squared. D, how much distance are we covering? 0.1 meters. And that's going to equal, starting at 0, plus how much is your velocity? 0, because that's vertical velocity, don't forget. Plus 1/2, 9.8 times t squared. You can make it negative, all that stuff. We're beyond that here, I hope. Anyways, your time is going to be 0.143 seconds. Final step now, can you put it all together? Did you? I hope so. Remember, distance is going to equal velocity times time, right? We have a velocity. Our velocity is 4.2. We have a time. Our time is 0.143. Multiply them together, and we are going to get 0.6 meters. Or since they're doing everything in centimeters, 60 centimeters. Awesome. All right, something to keep in mind as you're doing this. Remember, the shape of the container does not matter. It could be it could be hourglass shaped, as long as it goes up there. Right, it's the height, just like we talked about before when we did pressure and absolute pressure. All right, hey, that's it for today. Just make sure you're good with Bernoulli. We have Bernoulli's effect tomorrow. See you then.